All right, continuity, 2.6. The thing about continuity is I've been mentioning continuity since like the first day. And now we formally have the section on it. Here's the definition of continuity. F is continuous at x equals a if the limit as x goes to a of f of x equals f of a. In other words, you get what you expect to get. That's what continuity is. So every time you use the method of substitution to find the limit, you were just using the fact that it was continuous. Okay? And I mentioned this. But that's all it is. You get what you expect. The pre-calculus notion of what's happening at the point matches the calculus notion about the behavior as you approach the point. Those two things are the same. Right? And most things, you like continuous things. Right? Like you like that, oh, it seems to be warming up. You would not like that all of a sudden the weather changes and you walk outside and suddenly it's like, 45 degrees after being 70. Right? We don't like that kind of thing. The only place we like things that aren't continuous is password security. All right? So when you create a password and you don't want it to, you don't want the receiving end to accept a password that's close to the password you have. You follow? You want those things to be, what were they called? One of my buddies in grad school went into the NSA. And before he ended up doing stuff that was too classified, he used to come talk at math club. Was it called hatch functions? Was it hatch or hash? I forget. It's extremely discontinuous functions. All right. Now, when they teach this in like AP calculus, they come up with this continuity checklist. This one equation is saying at least 3 different things. In order for this equation to be true, first off, the function has to be defined there. Secondly, the limit exists. Now, in order for the limit to exist, what has to be true? This is why I say at least 3 things. For the limit to exist, the limit from either side has to exist, and they have to be what? Equal. So this alone has, I guess, 3 other checkpoints. And then, of course, you got to check they're equal. So if something is not continuous, it's called discontinuous. So the prefix here is dis. Dis meaning not in this case. If something is discontinuous, all you have to do is show it one of those things isn't true. Right? So to be continuous, all 3 of these things have to be true. So if one of those things isn't true, then it's not continuous. Okay? So for example, let's look at these 3 functions at these 3 points. So we're looking at x equals 2 here. The first thing you check for continuity is you try to plug in the number. So try to plug in 2. The numerator, 3 times 2 is what? 6. The denominator, 2 minus 2 is 0. So is it continuous? Not continuous. Why? Well, f of 2 doesn't even exist. But not only that, from direct substitution, what else can we say about it? We have a non-zero number divided by 0. So what did we learn yesterday? What does that mean limit-wise? What's going to happen? It's going to blow up. It's going to be unbounded. Right? So not only does the function value not exist, the limit doesn't even exist. So there's no hope for this function. Something's wrong with it. All right, let's take a look at g of 0. So we'll look at 0 here. G of 0. I get the sine of 0, which is divided by x. So once again, not continuous because the function value doesn't even exist. Now the fact that we get a 0 over 0 gives us hope that even though the function value doesn't exist, the limit itself might what? Exist. In fact, it does, because this is a limit we know. This is one of those special trig limits, right? As x goes to 0, sine x over x goes to what? 1. So unlike f of x, which is going to have vertical asymptote there at x equals 2, at least the g of x, yeah, f of g of 0 is not defined, but at least the limit exists, which means there's a what in the graph? There's a hole in the graph. Now let's look at h. Let's see. We're looking at x equals 1. Does h of 1 exist? Well, looking at here, what formula do I use when x equals 1? This one, right? So h of 1 exists. So now I have to look at the limit. And of course, as we go to 1, not 0. And of course, h is a piecewise function that's broken up at what x value? 1. So, to understand this limit, we got to look at the limits from either side. If we're coming into 1 from the left, are we plugging in things a little bigger than 1 or a little less than 1? A little less than 1. And if I'm plugging in values less than 1, which of these formulas do I use? The 3x. Whoop. Can I just plug that 1 in there? Yeah. So I can use principal substitution here. And get my limit here is what? 3. Now, coming into 1 from the right. Now I'm plugging in values a little bit what compared to 1? So what formula do I use for values bigger than 1? 2x squared. What's that work out to be? 2. Are those the same? Nope. So the limit as x goes to 1 of h of x does not exist, so h is not continuous. Okay? So we have the 3 different cases here. Number 1, neither function value nor the limit exists. Number 2, the function value doesn't exist, but the limit does. And number 3, the function value exists, but the limit what? Does not. So those are all the different combinations of how a function cannot be continuous. All right, let's take a look at example 2 here. So I'll let you write this down. I'm going to fire up Desmos here. And put this in Desmos. You can do this in Desmos. It's pretty cool. So to get piecewise in Desmos, we're using the squirrely brackets. We have x less than or equal to 4, colon, x squared minus 3x plus 1, comma, x greater than 4, colon, cx plus 7, parenthesis, add a slider c, and we're looking near x equals 4. So once again, we'll do the there you go. And we can see what's going on here. Okay. Now, if we think about the structure of this function, the cx plus 7 is what kind of function? Its graph is a what? It's a line. The slope of that line is what the c is. You follow? So the c is just going to be controlling this. So check this out. So as I move c around, pay attention to the line there. You see how that works? Now what we're trying to do is we're trying to figure out the value of c so that the function's continuous. So if the function's continuous, then that means what? Everything matches up. You follow? So what continuous looks like this is how they often describe it. Right? So sometimes they describe continuous functions as functions that you can graph without having to lift up your pencil. You follow? The limit exists, and it's the actual function value. And so you just move right on through it. You follow? There's no jumps, there's no asymptotes, there's no holes in the graph. It's a smooth ride through. So that's what we're trying to figure out, what that value of c is. So how can we do that? Based on our calculations here, it looks like c equals -0.5. But how would we actually go about proving this? So let's look at the function here. And we'll recopy it. F of x equals x squared minus 3x plus 1. If x is less than or equal to 4, cx plus 7 if x is bigger than 4. Okay? So let's go through the continuity checklist. F of 4. What is f of 4? When x is actually equal to 4, what formula do I use? The top one. And so when the dust settles, what do you get from that? What's that? 5? Yeah, 16 minus 12 plus 1, right? 5. All right, now I need to look at the limit as x goes to 4 of f of x. And of course, this is a piecewise function where the conditions are broken up at x equals 4. So that means I have to look at this limit from what? Both directions. Yeah, plus and minus directions. So coming into 4 from the left, we're going to get 5. So that already matches up. So we're good on that. What do we get when we come in from the right? We come into 4 from the right. What formula are we using for the function? Yeah, the cx plus 7. Now don't let that c freak you out. That c is not a variable. It's a constant. It's a parameter. The limit is on the x. So as x goes to 4 from the right, what's my answer going to be here? You're plugging in x equals 4. So your answer is going to be what? Yeah, 4c plus 7. Does that make sense or not? Okay. Now in order for this to be continuous, the function value has to match the limit. The limit from the left is already good. The limit from the right is the one I need to work on. You follow? So what has to be true to make all these things equal? Yep. That has to be 4c plus 7 has to be 5. Make sense or not? So you go through your standard subtracting your 7 off, divide into 4. And lo and behold, what do we get? Boom. Which is what we had guesstimated on Desmos. Okay? So this is like the ultimate piecewise problem because it, do you know how piecewise functions work algebraically? Do you know how limits work left and right? Do you know what continuity means? All comes together. Okay, I did a couple of these in the homework. Any questions on this example? All right. So let's talk about types of discontinuity. So there are two basic types of discontinuity. So discontinuity. There's sort of the mild case. The mild case is the limit itself exists. So if the limit exists and we're discontinuous, then the only way that can happen is what? So that means that, if the limit exists, that means either that the function itself doesn't exist or the function doesn't equal the limit. These types of discontinuities are called removable. So graphically, here's your function. The limit exists. Oops. Either the function isn't defined or they've defined the function in the wrong place. You follow? So these are fixable. What do? You just redefine the function where it should be. You follow? That's removable discontinuity. The limit exists. Either the function doesn't exist or the function's in the wrong place. So we can remove the removable discontinuity by defining the function to be the same as the limit value. So basically what we would do is go up here and we'd fix it. We would just patch it in. We'd say, no, that's the wrong place. You missed. You patch it in. Follow? Removable. Make sense or not? So if the one is called removable where the limit exists, then what's the other case? Non-removable. Or sometimes this is called an essential discontinuity. Essential meaning there's something inherent in the function that breaks it. There's no quick fixes here. So this is the extreme case. The limit does not exist. So these are non-removable. They're non-fixable. And it's the same limit not existing stuff we saw way back on Monday. All right? What's one way for a function not to exist? The graph could do what? It could have a jump. It could do what? It could go to infinity. It could have vertical asymptote, right? Or it could do what? Yeah, it could just oscillate and not settle down. So those are endemic to the function. It's in the function's DNA. You can't fix that. All right. You just move on. So looking back at our three functions from example 1, this has a non-removable infinite discontinuity. You follow? Number 2, the g of x has a removable discontinuity. Since the limit exists and is 1, we can remove it by just making g of x a piecewise function. So here's how we do that. Since the limit as x goes to 0 of sine of x over x equals 1, here's what we're going to do. We're going to take our g of x as we were given to us. Sine x over x is perfectly fine as long as x isn't 0. But now, this is the new part. if x is 0, I know what the function should be. The function at 0 should be what? 1. So I'll fix it. Okay? Now, technically speaking, this is a different function g than we had before, because the g itself we had before plain wasn't, So, I mean, a lot of times you'll see, it depends on the book you use, they'll just fancy this up. They'll call this like g hat or something, or maybe g tilde. Because technically, or g, well, I guess g bar. Technically, this function's different than the original g, because you have it defined at 0, but that's too pedantic for me for Calc 1. Okay, just fix it. One of my students, it was last year before, what's it called? There's this infomercial product where there's like this tub leaking water, and they just take this tape and they slap it on. Yeah, Flex Seal or something like that, or Flex Tape. That's all you're doing. You're just smacking it on, fixing it. Now, if we look at what was going on with H, so the deal with H, the limit didn't exist. But the reason, I'm sorry, we were going to 4. Excuse me, we were going to 1, not 4. But the reason the limit didn't exist at H, we didn't get infinities out, but we just got two different numbers. So we had a jump happening. And if we graph H, then here's something to make note of here. Notice that H of 1 itself was defined to be 2. So H of 1 was defined to be 2, which was the limit as we came into 1 from the right. But coming in from the left, the limit was 3. Okay, so we still have a non-removable jump discontinuity here. Okay. That being said, if I only looked at coming in from the right-hand side, if I come in from the right-hand side, I do actually hit the function value. You follow? So just like we had one-sided limits on Monday, we have one-sided continuity. So even though H is not continuous at 1, we would say H is continuous from the right at x equals 1. Because the limit as x comes into 1 from the right of h of x is h of 1. So you can have one-sided continuity. And so here's the pictures for that. So once again, as you go through this course, you're going to have theorems and concepts that you're going to be able to write down, but it's really helpful if you have pictures in your head that go with them. You follow? And a lot of what you do is, here's the picture, what's the concept? Here's the concept, what's the picture? So here's continuity from the left. So as you come in from the left, the graph is going to actually hit the dots filled in from the left. Continuity from the right, as you come in from the right, the dots filled in from the right. You see the difference? And if you're continuous from the left and continuous from the right, then you're going to be continuous, period. Okay? All right, so instead of focusing on the places where things go wrong, let's talk about where it goes right. So typically when you have your function, we live in a very specialized world here in Calc 1, because when functions go wrong for us in Calc 1, they only go wrong at a couple different places. There are functions that are terrible everywhere. It's stuff you see as a junior math major will just blow your mind. All right, intervals of continuity. So let's take a look at this function. Now, I want to say up front, I think on your handout, on the printed handout, I think this is different than on your hand. This is correct. On your handout, is it flipped? Yeah. Yeah, so this is correct. So fix this. So intervals of continuity are exactly what they say. It's where is the function continuous? The intervals are real numbers. All right. So let's take a look. Now this is like something out of Desmos. So there's things that we're are assuming. Like for example, when you see this, we're going to assume that that goes on that way forever. Okay. And that there's no other jumps or anything else out there. You follow? And the same here. And the same here. So with that being said, let's travel along the x-axis and look at where the function's continuous. So it's going to be perfectly fine up until it gets to this vertical line, right? And that vertical line is at what x value? 1. -1. So this is our first interval of continuity. Does that make sense? So intervals of continuity, these intervals are on the x-axis. We want to know the x values for where the function is continuous. Now we pick up at -1, and we're going to be good up until here. You follow? Notice, look at the endpoints. You follow? The endpoint matches up at the start of this interval, and the endpoint matches up at the end of this interval. So notice on the interval of continuity, we have it with brackets. You follow? So just like brackets include, parentheses don't, that's the same thing happening here. You follow or not? So the endpoints get included here. So this is saying that we are continuous from the right at x equals -1 and continuous from the left at x equals 2, because those dots are filled in. We cool on the brackets as opposed to parentheses. Okay. Now we move over from 2 to 4. We're looking at this part of the graph. Notice we've got an open circle there, so on our interval of continuity we have a what? Parenthesis. The 3 is filled in, so we have a bracket. And then last but not least here, we move from 4 off to infinity. We look at this. So open bracket at 3 rather, not 4. Off to infinity. Okay? So looking at the graph, do the intervals of continuity make sense? Do you see why we're using the bracket versus parentheses? Okay. Now back in the day, you might be familiar with this symbol. This symbol. That the union symbol, right? Like with domains and stuff. We don't do that with intervals of continuity. We list them out. We just list them out. Okay. Here's why we don't use the union symbol. If you write -infinity to -1, union -1 to 2, -1 to 2, this is talking about the union of two sets. We're just lumping all these things together. And if you just lump all these things together, that's all the numbers from -infinity to 2. You follow? Because even though I don't have -1 here, I do have -1 here. But you see, if I wrote this down as the interval of continuity, this would suggest that we're continuous at -1, which we're not. Okay? So, we list intervals of continuity. So we separate with commas. Oops, commas. We don't use unions. Because, once again, that bracket gives us a directionality of continuity that the set theory stuff doesn't care about. Okay. So I mean, that's half the battle, is we have all these amazing concepts and we have to try to codify them somehow, and we have to be very precise with the language. That's why it's hard, because like no one did anyone grow up with spelling tests? We're like the last generation to have spelling tests, because it's just Google spells for us, or does it? The thing all the times autocorrect screws up. What's funny is, and what's spooky is, one of my buddies on Twitch, we call him Clown with a K. Anytime I type clown in, no matter what, it autocorrects to capital K Clown. All right, you know best. So looking at our three functions, the first one, we've got that infinite discontinuity at 2. So otherwise everything's fine. That would be the intervals of continuity for that one. For g of x, before we fix it, everything's fine except at 0. And for the h of x, we would write that 1 because it is continuous from the right. Okay. So here's your video going through 3 more examples talking about intervals of continuity. Number 1 is nice because it has a non-removable one and a removable one, and then we go through and talk about how we have to fix it and define it. And then these other ones, we've seen these other ones throughout. And then number 6 says, okay, go backwards. Here's some information about the function. Can you make the graph that goes along with it? All right. So I really like these ones because you have to put things together. All right, properties of continuous functions. Bless you. Combinations of continuous functions are continuous. So if you add and subtract continuous functions, they're going to be continuous. Why? Because limits respect adding and subtracting, and function arithmetic respects adding and subtracting. You can multiply and divide continuous functions as long as you're not trying to divide by what? So those will be continuous. And composition of continuous functions are continuous. You plug a continuous function into a continuous function, you're going to get a continuous function. Another big property of continuous functions is the intermediate value theorem. This is a video, but I can give you, here's a picture for the intermediate value theorem. But let me give you an example of the intermediate value theorem. Right? I walked my dog this morning, it was 53 degrees Fahrenheit. Right? Let's say I go home and it's 72 degrees Fahrenheit. Do you believe at some point between this morning and when I get home, the temperature was exactly 60 degrees Fahrenheit? Because you think the temperature is going to gradually increase, right? It's going to continually increase. And so that temperature value, that 60 degrees Fahrenheit, is an intermediate output value. It's an intermediate temperature value that has to come sometime between the intermediate time between when I walked my dog and I came home. Does that make sense? That's what the intermediate value theorem says. It says this. If f is continuous on the interval AB, and you have a d value between f of A and f of B. So here's the setup. Remember, these are y values. So f of A is a y value, f of B is a y value. D is an intermediate y value. Okay? Now, I'm assuming f is continuous. What does that mean graphically? That means that we're going to start at this point and we're going to end at this point. And since f is continuous, you can draw that graph without picking up your pencil. You follow? So I'm going to draw this graph without picking up my pencil. Oh my goodness. So the intermediate value theorem says if you pick any intermediate y value, right? So here's the intermediate y value. At some point, you're going to have the graph cross that point. And then it will come from an intermediate x value. There is a C between A and B. So f of C is D. So intermediate y values come from intermediate x values. That's the intermediate value theorem. It's working backwards. Intermediate y values come from intermediate x values. And this is something that, even though hopefully it makes sense, in order to prove it, we would need to dive deeply into what the real numbers are and structural properties of the real numbers, which we don't dive into. Okay, we just don't do that in this class. All right? It's an important theorem. We will use it to prove other important theorems in this course. So intermediate y values come from intermediate x values. That's intermediate value theorem. Intermediate outputs come from intermediate inputs. And here's the classic example here. It's a video where you use the intermediate value theorem to help you find x-intercepts. So there's a thing called the bisection method we talk about. Back in the day, you had a graphing calculator. You could try to find the x-intercept of something by looking at sign changes. So that's an application of the intermediate value theorem. Here's a more robust example that's a little counterintuitive. If you assume the temperature is a continuous function, at any point, at any time, there are two antipodal points on the Earth that have the exact same temperature. What's antipodal mean? Like they're on opposite points, right? Like North and South Pole are antipodal. So you believe that? At this given time, there are 2 points on the planet that are complete opposites that have the exact same temperature. You can use the intermediate value theorem to prove it. Another example, it's an application of this, is called the fixed point theorem. If I had a map of Ohio on the floor, then there's at least 1 point. There's at least 1 point on the map that's directly above its corresponding point on the floor. So if there's a point on the floor directly below its corresponding point on the map. That's called the fixed point theorem. Or it's fixed point theorem. Anyway, here's your homework. Okay.